Okay. And group three.
Uh, we have done some basic work, but we don't know whether it is correct or not. So, can I share my screen?
Yes. Go ahead. Do I have to give you permission to share the screen or?
Let me check.
Oh yeah, I can see it.
Yeah, yes,
It's loading.
it's the
Okay.
it's the result we have now so far, and I wonder that is there anything we can do next to uh, improve or adjustment about the code or to make it uh, satisfy the requirement of uh, the challenge of the
Okay.
task.
First, tell me what's your setup. What's the data set
Um,
you're using? What's the model you're using? Optimizers, hyperparameters.
uh, I use optimizer based. I use this one. I'm sorry, this one. Uh, just SGD. And I haven't tried other kind of optimizer yet.
Okay, so you've using stochastic gradient descent with
Yeah.
a multi-layer perceptron. What's the size of the multi-layer?
Uh, Let me check about that. Here, this is the size of
So it's a four-layer MLP.
yeah.
Oh, you're training on the MNIST dataset?
Yes, is that correct for the task member
I
that I
haven't
tried
read
to
the I haven't read the PDF. I was just told that you need to do backpropagation.
oh, all right. I think
Okay, so for this stochastic gradient descent, are you using what's the learning rate? Are you gonna use different learning rates or are you just gonna stick to the same one?
so okay. I'll try to learning rate and see how it look, how it improved
Also
the accuracy.
also with the stochastic gradient descent, you have momentum.
Yes.
So you can also play around with the momentum. And in addition to that, you also have the atom optimizer, which uses both the first moment and the second moment to stabilize the training. You might want to also play around with that.
Hmm. Okay, I see. So
But the go ahead.
uh, so uh, so what I need to do is to um do research on the momentum and to try to deal with it and make it adjust it to in order to achieve better accuracy.
It's not, well, what you could do is try different type of optimizers
Hmm.
and then do a grid search for what's the best parameters for those optimizers, and then compare the performance of the different optimizers in terms of the accuracy of the test set, the how quick did it reach that accuracy in comparison to the optimizers, and what's the how close is the performance at the test in comparison to the training. Because in the previous class I was told you saw the difference between how sometimes the model is overconfident on the training, and then you notice that the validation set is just performs there's a huge gap between the performance of the test and the validation and the training. So you also want to how inspect that for the different types of optimizers.
Okay, I see. I will try with different optimizer and compare the result and find the best one. Okay, I think that's all. Thank you.
No problem. Ideally, additionally, you could go ahead and try this for multiple model types because you're just using right now a multi-layer perceptron. Dense
Mm.
layers are typically a very simple model. So once you start going more complex, you see a change of behavior, especially with the MNIST. The MNIST is a very simple data set, so you might not be able to see the huge change in performance between the different optimizers.
Okay, so try with different model structure and then maybe try some different optimizer.
Data set. Yeah, and different data set because the MNIST is just too easy.
Okay,
The You won't barely see a significant change in the performance.
see. Thank you.
Okay. Any other comments or questions?
I think that's all for our group.
Okay. Good luck. Group 4.
Here.
Okay, go ahead.
Okay, I am just researching on the PDF. I haven't found my members yet. I will do it maybe today or tomorrow. And I have some experiences on handling the dataset, the same dataset, but with CNN. So I would prefer to design a new model with Atom Optimizer to do the whole thing.
Okay.
Thanks.
What's your benchmark for this then?
What do you mean?
So ideally, you want to try multiple stuff instead
Yeah.
of just showing the result for one model and one optimizer and one data set. So what are you gonna do different?
I have another data set in application to indicate the obstacles on railways. So I would do
Mm-hmm.
with that data set and some image processing techniques.
Okay.
This is my
What model
opinion.
are you gonna use? You mentioned you're gonna use a CNN. Do you have a
Yeah, CNN.
specific model in mind?
A C, maybe some CNNs that designed by my own on my own.
Okay, so you're not gonna take like a model like that's already online, like the ResNet or the NASNet mobile or some other model.
Something modified from the net, but more complex. complex and maybe with some residual layers.
Mm-hmm. You just then are you gonna use one optimizer to, or you gonna see the performance change with different optimizers?
Maybe provide the standard by Atom Optimizer, then compare with SGD.
Okay.
Thanks.
Any questions or anything else you want to say?
Maybe not.
Okay. Lastly, group 5.
Hi. We've
Right.
only found our group member, and we're still researching on the topic. So we haven't do anything yet.
Okay. Do you have any ideas of what to do so far, or what do you want to do?
Yes, but not. We haven't know everything.
So, what are the ideas?
I'm only just read through the PDF, so I haven't have any idea yet.
But you've been listening to the previous conversations,
Yes,
so
but
you should sort of start getting an idea of what you're supposed to be doing.
oh yes, I know. It's about the optimizer and gradient descent.
Mm-hmm. It's mainly on the backpropagation aspect.
I'm sorry.
So
Can you repeat?
it's mainly on the backpropagation aspect. So with that in mind, do you have any idea of what you could do or what you want to do?
I think we're still looking onto it. So no ideas yet.
Okay. Any questions or comments then?
No, thank you.
Okay. Anybody else who hasn't spoken yet? Anybody who hasn't spoken who want to speak now? Well, let me put it this way. Does anybody have any questions or comments they would like to make about the homework or ideas you have about the homework but feel unsure about? Okay, go ahead, Henry. Henry.
Hey, hi TA. I would like to ask, are there any limitations about the selection of datasets for this challenge?
Well, do you have the PDF with you?
Yes, I have read the PDF file and I didn't see that it has mentioned any specific datasets.
Then there's no limitation with it. So long as you see anything that is reasonable. Go ahead, Sue.
Oh, okay. Hey guys, if you want the MNIST dataset in CSV, here's the Kaggle link. You know, just in case you want it in a spreadsheet or something. Is that what you're asking, Henry?
No, he's asking if there's any limitation on the choice for the data set they use for the home.
Okay. You want to use another dataset or something, Henry?
I just want to confirm whether there is an limitation. There is a limitation. Yeah.
Oh,
And
yeah.
the
Okay.
original one is suitable already. Yeah.
Yeah, sure. You have something in mind? Just what kind of dataset do you want to experiment on?
You mean what kind of data set?
Yeah, have you thought about it already?
I think all kinds of data sets that can be related to categorizing tasks are suitable for this challenge.
Yeah, of course. Okay. Yeah.
Okay, thank you.
Okay.
Well, any other questions, doubts, concerns? So wait, does the class usually last 2 hours in these situations?
It lasts 2 hours if we're presenting like officially, but today it's just like a progress report. So today's class is gonna be less long.
Okay. Well, if anybody has anything else to present or any questions and doubt, I'll be here for 20 more minutes. Otherwise, I believe the class can be dismissed, right?
Wait, guys. For what is it? Group four for challenge 1. Please submit your codes, reports, videos, or anything. Anything is okay to the Google file right now, please. Is group 4 here for challenge 1, not challenge 2?
Yeah, okay.
Oh, thank you.
I
Okay.
will submit.
Yeah. Anything's fine, and it's just that people need to do the evaluation form like right now, today.
Right now, okay. I will
And
inform them.
just surveying for this challenge. Have you found your teammates yet? Did they talk? Do you talk to each other?
You mean challenge 2?
Yeah.
Yes.
Oh, you have you guys have contacted each other, huh?
Yes, but I'm now in group 3.
Yeah, okay. Just checking.
Okay.
Just making sure you guys are talking, because some people from the last challenge didn't even fill out their contact info, and there's no way to contact some of them. But anyway, thank you.
Thank you.
Excuse me, Tia, I have a problem. That I want to ask about challenge 1. That is video report needed?
Oh, either or. If you want to organize it better, a video is better. You know, just the evaluation score is probably gonna be higher because
Oh.
video is more organized. Your thought process is more refined and things like that.
Oh,
But
okay.
yeah, but is it exam week already? The exams? Is it time for exam already?
Probably 1 week or 2 weeks later.
Oh yeah. Oh well, I guess you think about it yourself.
Oh,
Yeah, just make yeah,
okay.
make well whatever floats your boat. Okay, just be comfortable with what you choose. Okay, no no rush. Okay, yeah, and no, I'm not pushing you to do anything. Okay, sorry.
Okay,
Okay.
thank you. Thank
Okay.
you, Tim.
I think I kind of forgot. I need to do the background on some optimization methods, huh? So I'm gonna do it right now. Is that okay, Edwin? Okay.
Sure, go ahead.
So this is the background on some 3 second order optimization methods. I won't go into detail with the math right now, but yeah, here's the recap. So second order optimizations, they offer faster convergence to optimal solutions. And today, I'm gonna do the background introduction on Newton's method, the BFGS algorithm, or it's called by another name, which is the quasi-Newton's method, and the last one is conjugate gradient method. So optimization, it's crucial for improving making decisions as a computer in machine learning. Our goal is to determine the optimal model parameter values to minimize or maximize our objective functions. Well, in today's case, we want to we need to categorize the digits from the input images of those zeros and ones, and okay, understanding optimizations in machine learning. say we're finding the exit in a maze, it's more efficient if we used a map, a second order methods instead of just following the walls, which is just what standard ML does. Model optimization involves modifying the model to produce optimal predictions, and continuous function is used to minimize the loss functions or optimize the goal, the performance indicators. And here are some terminologies. A model, which is just a way for computers to understand and make predictions from the data. And optimizations is finding the best settings, the weights and biases for the program to make the most accurate predictions. And gradient descent, which is a method to find the best model by making small adjustments. The first order, or it's called the Jacobian, not called the Jacobian, utilizes the Jacobian matrix. It used the gradient indicating the path for the most development. And the second order, which used the Hessian matrix, providing the direction and curvature information. So the first thing is Newton's method. We need to compute the gradient and the Hessian matrix to calculate the optimal point. And this method can provide a rapid convergence to minimum or maximum of a function. Okay, we use Taylor expansion to expand our optimal function, the function like so. The second order is typically accepted, and we update our parameter as the formula right here on the fourth line. Now, the first order differentiation, it indicates the direction to reach the top, and while the second order indicates the steepness or like the curvature information that allows adjustments of step size. And here's a code snippet of the implementation. Now, here are the goods and bads about the Newton's method. The good is that it is efficient for like low dimensional problems. It requires less memory and appropriate if the Hessian is positive definite. But the negatives is, which is also about the Hessian matrix, because you need to find out the partial derivatives of the function, which requires for careful tuning and problematic for many saddle points. And it's computationally complex. Here's a example. If say we're optimizing the quadratic function x squared plus 2x and plus 1, we start from 10, and using the algorithm here, we can find that the minimal point is found at x equals -1, where the function is 0. You can plug in the numbers to fact check. Okay, now the BFGS algorithm, or the quasi-Newton algorithm, is an advanced optimization technique for more nonlinear problems. It only approximates the inverse Hessian matrix instead of just directly calculating it. The BFGS provides a way to perform optimizations similar to Newton's method, but without the heavy computations. This algorithm approximates the inverse of the Hessian matrix by another matrix called the MT. It uses an iterative process to refine an approximation. Now, here are the positives and the negatives. The positives is that BFGS adapts to the problem, converges efficiently without explicit Hessian computation, adapts to specific problems. While not as computationally expensive as Newton's method at times, but it moderately is also expensive. And it may not perform well in highly non-convex landscapes, and memory usage can increase with large data sets. Here's an example. Say we're optimizing the objective function x squared plus y squared plus xy plus 4. We start from the bottom right, which is 10. The coordinate is 10 and negative 10, and we use the algorithm like using the code snippet here. We found that the minimum is at 0, 0, where the value is 4. And finally, it's the conjugate gradient method. This is the optimization algorithm for large linear equation systems. It's suitable for large-scale unconstrained optimizations, optimization globally. Avoids direct computation of the inverse Hessian matrix, unlike the BFGS. It iteratively descends along the conjugate directions, and it looks at multiple directions to find the best path. And step size adjustment is to adjust how big or small the step should be. The pathfinding algorithm is kind of zigzag. It's like it takes the first guess, and the second step is to find it in the orthogonal direction, and so on. It's kind of zigzaggy. Okay. Here are the goods and bads about this method. It's guaranteed to converge to a good solution, and it works well for various purposes and less sensitive to noise. But it's slower than Newton's method and doesn't necessarily find the optimal solution to non-quadratic problems. Quadratic means like x squared functions like that, and it requires more iterations to find. So there are goods and bads about all three methods, and comparison is required. Okay, here's the example. We need to optimize the function, but this time in matrix form, ax equals b. Now, in matrix form, the quadratic function is ax squared minus bx, but there are no x squared. X squared is not the right way to address quadratic function in the context of matrix. You need to denote it like x transpose and ax and minus bx. We need to optimize it. And here the matrix of A and the B. The setting is as such, and the first guess is the dot in the middle. And first step it took is right here, and the second path it took is it bends lower and lower to the optimal point, which is at the coordinate 2, 2, and the value is negative 10. So the conclusion is the second order optimization improves performance and the speed and proficiency in the knowledge of these methods, while not including just these three methods. There are other methods, but the knowledge these three is beneficial, and these strategies converge faster and find better solutions using the second order differentiation information. So we know the curvature information, and it considered the problem features and computational resources when selecting the algorithm you want to use. all in all, the second order methods accelerate the search for optimal solutions in more complex problems than first order ones. Okay, so here's the quick comparison of the three methods today. The Newton's method is fast speed, high memory usage, but the complexity is also high. While the conjugate gradient is medium speed, low memory usage, and medium complexity. And the quasi-Newton or the BFGS is medium speed, medium memory usage, and medium complexity. Here's the implementation from scratch, but this is only the implementation of the first order, just to give you the idea what optimization means. Because the second order one, I think you guys should implement by yourself. Okay, so the backpropagation, it's the key to training neural networks. It helps the network learn from its mistakes and improve its performance. Without it, training neural networks would be impossible. So we always use neural network and train it using backpropagation. So the algorithm, in first stage, we need to forward pass. We need to feed the network the data through a network to obtain predictions, and we learn from its mistakes by differentiating the loss function to the respective weights, biases, and such to minimize the error to improve future predictions. The forward pass involves feeding input data, as we mentioned, which this step involves a series of dot products and activation functions. And the goal is to reach the output layer to obtain predictions. Now, the exclusive OR dataset is just like in the digital circuits. The output is one only when the input x0, x1 is different. The goal is to train a network that can correctly predict the output of any given input. Now, the network architecture of the implementation in the repository is like this. It's 2-1 network. It means 2 input nodes and 2 hidden nodes and 1 output node. And we also need to include a bias term. We can be done 2 ways. We can use it separately or treat the bias as a trainable parameter also. We can treat the bias as a trainable parameter by inserting the column once into the feature vector in the context of the exclusive OR dataset. And this simplifies the implementation and makes training more efficient. But we need to remember that in the final output, it does not require a bias. Okay, the forward pass in action. Oh, oh no, the image is not here. Okay. Sorry guys, this value, shoot. I forgot to paste the image. Okay, just use your imagination on this one. We initialize the weights in our networks and we feed it in the input layer, and the value represents the current weight for a given node, and we use backpropagation to minimize the error. So I won't be diving into the math part today, just the idea. And I think it's better to show the, just show the code. Sorry guys. Damn it, where's the? Yeah, okay. So here's the repo. I think I'll send the link later. Okay. Okay, so here's the algorithm of the neural network. We have the activation functions here, the sigmoid function, and the derivative function. And we capture the information by calculating and storing the loss and minimizing it to our prediction right here. And how do we calculate the loss? We use the mean square error right here. Okay, so the summary is backpropagation is a generalization of gradient descent in the family of algorithms. It's specifically used to train MLPs, and there are two stages: the forward propagation and the backward propagation, the backward pass. And that wraps up my presentation on this.
Any more questions? Okay, if there's no more questions, we could wrap up the class. Okay. Class is dismissed. Go enjoy the rest of the extra hour you guys have now.